Hey there students, Mr. Cowell here. Today we're going to be talking about multi-mass systems, which means the interacting forces between multiple objects that are in contact with one another. It's a really sciencey way of saying things touching, what happens. We're going to start off this explanation with a story, as we like to do. This is Phil. Say hi to Phil. Nice job. So Phil is at the bus stop one day waiting for his bus when his good friend Hank walks out. Hank says, "Hey Phil, how's it going?" Phil says, "Hi, how are you?" And they say, "Good, good," and exchange pleasantries for a moment, and then there's an awkward silence. And then Hank remembers, "Oh, Phil, I heard you got a new cell phone. Can I see it?" Phil says, "Oh yeah, here it is. It's the iPhone 17. It's the size of my face. It can compute pi to infinite decimals. It's great. Love my new iPhone." Hank says, "Oh, cool, iPhone, huh? I actually got the newest Droid just the other day." Phil says, "Oh, Droid, huh? Let's see that." Hank says, "Come on out, Droid." So Hank's Droid comes out. Phil is simultaneously impressed and a bit intimidated and says, "Whoa, Hank, I didn't know that droids came out with a model with a weapon. Interesting." Hank says, "Yeah, it's pretty cool. Works for self-defense and for calling my grandma. You know, making a list of groceries and things like that." And Phil is still a bit intimidated and says, "Hey, you mind having it point its gun somewhere else?" And Hank says, "It's fine, it's fine. These things have been found to explode very rarely." And Phil says, "What?" And Hank says, "Don't worry, I'm sure nothing will happen." And then all of a sudden, and Phil gets very, very anxious at this point. And Hank says, "No, don't worry, there's nothing." And the droid explodes. Massive explosion sends Phil and Hank both flying. Phil is a bit smaller, Hank is a bit larger. What will happen to the two of them after they've been affected by this common force? That's what we'll investigate here. Here's a little bit of information about Phil and Hank. Hank, being the larger gentleman, has a mass of 89 kilograms. Phil, being the smaller gentleman, has a mass of 67 kilograms. And I'll give you a bit of information about Hank's motion in this case. After this force moved his body to the left, the result is he accelerated to the left with a precise amount of speeding up. We would say that he gained 3.8 meters per second each second in the negative direction, because we commonly say that left is the negative direction for no reason other than to make sure we're all being consistent. So we now have the mass and acceleration of Hank. We have the mass of Phil, but not the acceleration. That's therefore going to be our question. With what acceleration will Phil speed up in the opposite direction from Hank? The key to this is going to be that the explosion is common between them. And we can assume that equal and opposite forces were put onto both of these men. So, what can we do? Well, we have this magical equation that we like to use once in a while. We call it F equals ma, and it's our good little buddy, and we're going to be using it quite a bit. And we can use this equation and the variables that we have to figure out the acceleration of one of the objects if we don't have enough information. So, here's what we'll start with. We know that the force that's put onto Hank is equal to the mass of Hank multiplied by the acceleration of Hank, which resulted from the force on Hank. So all these variables are related by the equation F equals ma. We're going to specify the information just for Hank first. So if we wanted to know how much force exactly was put onto Hank as he was thrown aside, then we'll need to multiply his mass by his acceleration. So let's do that. Let's plug in for his mass, it was 89 kilograms. Let's plug in for his acceleration, it was negative 3.8. And the only significance, again, of that negative is that he's moving in the negative direction. Okay, he's not doing opposite motion or something like he's turning inside out. A lot of people get a little jittery when they see the negative and they're like, "Oh God, what does that mean?" It just means in the negative direction. That's it. So we take those two numbers, we put them in our calculator, we multiply them, and what we get is negative 338.2, and our unit is the Newton, because this is a force. So now we've established how much force that explosion put onto Hank's body, or at least this is the net force on his body as a result of the explosion. So, okay, that's useful, I guess, but that's not what our answer is supposed to be. It's supposed to be the acceleration of Phil, who we haven't even talked about yet. So why is this useful that we went with Hank first? Well, because forces are supposed to be equal and opposite. Action-reaction pairs, we've talked about that before, and this is an example where one type of force we can assume is evenly distributed in all directions. The explosion goes up, it goes down, it goes left, it goes right, and that means that if that's the amount of force put onto Hank, then an equal and opposite force should have also been put onto Phil. So now that we know the force on Hank, we also know the force on Phil. We can assume safely that it is also 338.2 newtons, but in the positive direction, because it's equal and opposite in direction. That is very useful information, because again, F equals ma only has 3 variables, and now it seems like we've got 2 of them that can be used for Phil, so we can now find the third variable. So let's do that. Let's use the equation in a more manipulated way. A equals F over m. That's just a simple algebraic reimagining of F equals ma. And let's specify that we're going to use information for Phil this time. So we put little subscript p's all over the equation. There's p all over this equation. Ew, gross. Okay, so let's plug in our variables. The force that we're assuming is put onto Phil is 338.2, and it's now a positive number, so we can plug that in. And the mass we were given right from the get-go is 67 kilograms. That is Phil's mass. That's how much matter he has in his body. Put that in your calculator, and you get a number 5.047, and then a bunch of other numbers, ... What we tend to do in our physics class is we like to use something called significant figures, and you may be already familiar with the concept, but we're trying to maintain the level of accuracy that the numbers at the beginning of the problem had. We can't take inaccurate numbers and put them together and somehow get something extremely accurate. There's no real way to do that scientifically, so we're going to try and maintain accuracy by using the same amount of significant figures in our answer as we do in the original numbers. So I look back to the numbers, I see 89, 67, 3.8, and all of those numbers from the original information had 2 significant figures. So even though this acceleration, this AP here, that's our final answer, we can't just write out these infinite decimals that our calculator gives us. We have to round it to sig figs, and it looks like 2 sig figs is what we're going to round to. So 5.047 whatever, that will round to 5.0 as opposed to 5.1 because that 4 is going to round down. And the 7 rounding up the 4 to a 5 and rounding the 5 up to a 1 doesn't work that way. You just pick one time, you round once with one number, that'll decide. So 5.0 is going to be our answer, and if we use the correct unit, then our full final answer is the acceleration of Phil is equal to 5.0 meters per second squared. And note that usually I state some kind of direction with acceleration. I've actually done that this time by only having a positive number. That's it, because the way that direction was shown originally was negative 3.8. Now that we have positive 5, it's implied that we're moving in the positive direction. So no need to say to the right or anything like that. We're all good. We can leave it just like this. So one more example real quick. There are 2 carts. There's a 1 kilogram cart moving this way and a 2 kilogram cart moving this way. Something's going to happen. They are forced apart by a spring, and you can imagine that the spring that's connecting them was compressed, and then someone releases it, and the carts are allowed to move apart. Just like the explosion in the last example, that's an example of a common force. So we can assume that both are given the same amount of force, equal but opposite, acting in opposite directions. Here's some information. The smaller cart, the one that has a mass of 1 kilogram, is accelerating as a result of that force at 3.6 meters per second squared to the left. So now you can see how direction is being established in this problem. They're not saying negative to show that it's going that way. They're saying left. That means our answer is going to need to have the word left or right or something like that rather than plus or minus to show direction. So we have the acceleration of one of the carts. We also have the mass. You can see where this is going. It's going to be just like the previous problem. So let's go through this one a little bit quicker. We're going to try and find out what is the acceleration of the other cart if we know the acceleration and mass of the first one. So let's get to it. F equals ma. That's an equation we know how to use. Let's try and find out the force that was put onto the cart that we have more information on. Let's just fill in the gaps for what we know. Force is equal to mass times acceleration. We know that the mass of this smaller cart is 1 kilogram. We know that the acceleration is 3.6, and I'm not even worrying about the word left right now. We'll work out that later. 1 times 3.6, hopefully you don't need a calculator for that. If you do, I don't know what to tell you. And the answer, of course, is 3.6 newtons, and even though this isn't our final answer, I'm just kind of keeping things tidy here, and I'm reminding myself that this is 3.6 newtons to the left, because if I know that that's the force to the left that the spring caused when it unfurled, then 3.6 newtons is also the force it provided to the right. So That means that's the force on the other cart. Now we have more information about the other cart. We now know the mass is 2 kilograms, and we know the force because we can assume it's the same as the other force. So, if we want to know the acceleration, all we need to do is plug in force divided by mass. That's just F equals ma manipulated around. The force we're assuming on the larger cart is 3.6 newtons. The mass we were told is 2 kilograms. That gives us 1.8. And you'd think that would be our answer, but again, we have to look back to our original numbers and see how many sig figs did we have. Because we can't take inaccurate data and turn that into extremely accurate data out of thin air. You can't do it. It's not scientifically sound. So we have 1, we have 2, and we have 3.6. Those were the numbers we were given. We have to go with the weakest link when we're looking for numbers with significant figures. So that means 1 sig fig is what we're going to be stuck with, because the 1 has 1 sig fig and the 2 has 1 sig fig. So even though the 3.6 has 2 sig figs, doesn't matter. We have to go with our weakest link. So instead of 1.8 meters per second squared, which is what we would love our answer to be, it actually has to be 2 meters per second squared to the right. We're establishing our direction by saying right, because they said left at the beginning, so they were telling us how to show direction. And we're saying 2 instead of 1.8 because we're forced to use one significant figure here. We're trying to maintain the amount of accuracy in the original numbers. And that 1 and that 2, someone could have rounded them. Maybe it's 1.9, maybe it's 2.1, but somebody just said, let's call it 2. So we're not really confident in those numbers, whereas the 3.6, we feel a little more confident in that original number. We've got to go with our weakest link, though. So as much as we would love for our answer to be 1.8, it's actually got to be 2. That's going to be frustrating for some people the first couple times you use it, but it is honest and it's scientifically sound. So that's all there is to it.